so far we are completed alkanes and alkenes, alkenes completed and alkynes completed. Now we are going to discuss that is alkynes, that is the third topic in hydrocarbons, that is alkynes. Yes. Alkynes are unsaturated hydrocarbons which contains C triple bond C. These are the alkynes. In this one the carbon hybridization is sp, whereas in alkenes carbon hybridization is sp2 and alkanes carbon hybridization is sp3. Here carbon hybridization is sp3, here the bond angle is 180 degrees and the molecule is linear molecule, whereas in alkenes the bond angle is 120 degrees and the bond molecule is trigonal planar, and whereas in alkanes the bond angle is 109 degrees to 8 minutes and the shape is tetrahedral. Alkenes completed. Now we are continuing this alkynes. Here in alkynes C triple bond C, the bond length of carbon C triple bond C is 1.20 angstroms, whereas in alkanes carbon-carbon bond length is 1.54 angstroms, in alkenes 1.34 angstroms, and here this is 1.20 angstroms. As the number of bonds between carbon atoms increases, bond length decreases, that is 1.54, 1.34, this is 1.20. So now we are going to discuss that is methods of preparation of alkynes. In these methods of preparation of alkynes, the first one is that is from dihalogenated compounds, So we are preparing alkynes from dihalogenated compounds. So these dihalogenated compounds are mainly two types, that is vicinal dihalides, and one more is geminal dihalides, vicinal dihalides and geminal dihalides. So what is vicinal dihalides? Vicinal dihalides means here two halogens are present on adjacent carbon atoms, this is called vicinal. That is, this is not nothing but 1, 2, that is example CH3, CHCl, CH2Cl. Here two halogens are present in adjacent carbon 1, 2, this is called vicinal dihalides. Geminal dihalides, in geminal dihalides here two halogens are present at the same carbon atom, that is called 1, 1. Here CH3, CH, this is Cl, this is 1, 1, this is nothing but geminal dihalides, So now we are going to prepare alkynes from dihalogenated compounds. This is nothing but this is called double dehydrohalogenation. Double dehydrohalogenation, that means two X are eliminated. Therefore, this is called double dehydrohalogenations. Here double dehydrohalogenation, here we need a very strong base just like NaNH2. So now we are going to prepare that compounds by using geminal dihalides and vicinal dihalides. Let us take the example, that is CH3, CHCl, this is CH2Cl. Sir, if you use alcoholic KOH, you use alcoholic KOH, or otherwise NaNH2. What we get? This is CH3, C triple bond CH. In this mechanism, what happens? The mechanism CH3, CHCl, this is CH2Cl. First of all, here we are treated with alcoholic KOH, this is actually this is which mechanism? This is E2 mechanism. We are using strong base OH minus, NH2 minus, these are strong bases. If we use strong bases, that follows E2 mechanism. With respect to this Cl, this is beta, with respect to Cl, this is beta. This is abstracting this proton, and what we get here, this is CH3, CH, this is it is abstracting OH minus and this is H, and this is eliminated CH, this is CHCl. This is in the first step we are using alcoholic KOH, but in the second step, to remove this hydrogen, we need drastic conditions. Therefore, not a normal alcoholic KOH is not used. In this one, we are using NaNH2. The basic nature of NaNH2 is greater than alcoholic KOH. This NaNH2, this is NH2 minus, this one abstract this proton, and here one more what happens, this is CH3, C triple bond CH, this is formed NaNH2. Okay. So, actually here in this one more drawback, that is if we use excess of NaNH2, this NH2 minus, this subtract this proton also, and we get CH3 𝗔𝗏 minus Na plus. So, and following acidification, that is in neutral medium NH4Cl by water, what happens, this one abstract water H plus from water, we get this is alkyne. So, in this one we are using double dehydrohalogenation. Alcoholic KOH 1,2 dialo, this we get, that is Na, this compound again. In the second step, we want the strong base when compared to alcoholic KOH, therefore we are using NaNH2. So, here if we use terminal alkynes are formed, then 3 moles of NaNH2 is utilized. Non-terminal we get, that is 2 moles of NaNH2 is required. So, in this one here we are important, this is a double dehydrohalogenation. Double dehydrohalogenation required drastic condition, not normal conditions. Therefore, the first step we are using alcoholic KOH, in the second step we are using NaNH2. So, NaNH2 is strong base when compared to alcoholic KOH. Sir, alcoholic KOH use cheyachu. Alcoholic KOH use chesinappudu temperature high ga use chesinappudu, high temperature 300 degrees Celsius ala temperature use chesinappudu double dehydrohalogenation aitundi. Kaani general ga NaNH2 use chesinappudu low temperature lo reaction jarugutundi. Right. So, this is preparation of that is alkynes from the dihalogenated compounds. So, after this one from dihalogenated compounds, the next one is, so the second one is, that is trihalogenated compounds. This is 1, 1, 1, 1, 1, trihalogenated compounds. Suppose if you use iodoform CHI3 when it is treated with silver on heating. So, here 2 moles we get, that is acetylene CH triple bond CH plus 6AgI. So, or otherwise this is iodoform is converted into acetylene. Sir, if we use this one CH3 Ci, this is I. This is triiodoethane when it is treated with silver. So, take 6 moles of silver and take 1 more mole of triiodoethane. So, what happens here? This is 6AgI. This is 6AgI is eliminated. So, what we get? This is CH3 C triple bond C CH3. This is a, we get butane is formed. Plus the byproduct is 6AgI. This is the trihalogenated compounds. After trihalogenated compounds, next one is, third one is from tetrahalogenated compounds. This tetrahalogenated compounds can be converted into alkynes. So, here tetrahalogenated compounds, that is take this example CH3 CCl, this is a CH3. When it is treated with zinc, ethyl alcohol or acetic acid, sodium iodide acetone. So, this is a dehalogenation. Here this is also E2 elimination reaction. What happens here? So, we get this C2Cls are eliminated, this 2Cls is also eliminated, we get CH3 C triple bond C CH3. So, this is 2, 2, 3, 3 tetrachlorobutane is converted into but2-ine. 2, 2, 3, 3 tetrachlorobutane is converted into but2-ine. Next, so here this is a but2-ine is formed. Actually suppose if you take CHCl, Cl single bond CHCl, this is CHCl. So, if it is treated with zinc, so we get acetylene CH triple bond CH. So, this is tetrahalogenated compounds. It is preparation of alkynes from tetrahalogenated compounds completed. First one is dihalogenated compounds, second one is trihalogenated compounds, third one is tetrahalogenated compounds, and the fourth one is, this is from carbides. from carbides. Carbides, that is calcium carbide CaC2, calcium carbide on hydrolysis we get that is CH triple bond CH plus that is calcium hydroxide. This is a calcium carbide, this is a acetylene. Suppose if you take Mg2C3, this is called magnesium carbide. When magnesium carbide on hydrolysis, we get CH3 C triple bond CH plus magnesium hydroxide. This is a propine is formed. Next, suppose if you take beryllium carbide on hydrolysis, we get methane CH4 plus 2BeOH taken twice. So if you take aluminum carbide Al4C3 plus H2O, here we get CH4 plus AlOH taken thrice. By carbides we can prepare alkynes and also alkanes. Beryllium carbide and aluminum carbide on hydrolysis it gives methane, whereas calcium carbide gives on hydrolysis it gives acetylene, magnesium carbide on hydrolysis it gives propine. That means carbide on hydrolysis we get alkynes as well as alkanes. This is alkyne and this is alkane. So these two are called methanides. This is called acetylides. This is called acetylide. This is allylide. This is acetylide. This is allylide. This is methanides. So after this from carbides, next one is from fourth one. This is coal-based electrolysis. Coal-based electrolysis, it is used for the preparation of alkanes, alkenes and alkynes. If we take C double bond C, this is H, COONA, this is called sodium maleate, or C double bond C, H, COONA. This is called sodium fumarate. Sodium maleate or sodium fumarate, you take anything. On electrolysis, aqueous solution on electrolysis. On electrolysis, this is converted into CH triple bond CH. Actually, this one follows free radical mechanism plus CO2 plus NaOH, that is NaOH plus H2 gas. This is acetylene. That means sodium maleate or sodium fumarate, when any compound is subjected to coal-based electrolysis, we get acetylene. So this sodium maleate and sodium fumarate both are geometrical isomers. Sodium maleate and sodium fumarate both are geometrical isomers. This is coal-based electrolysis. So after coal-based electrolysis, next one is from alpha diketones. So alpha diketones, take this one, this is alpha diketone. This alpha diketone, when it is treated with hydrazine NH2, here we need 2 moles. Here addition of water molecule, this is a nucleophilic addition and followed by elimination, this is called condensation reactions. Carbonyl compounds undergoes condensation reaction. Here 2 moles, so we get here, this is double bond N NH2, here also double bond N NH2. This is nothing but this is called bis hydrazone. So now this is treated with HGO, water molecule, loss of water molecule takes place. This is double bond N, here double bond N, this is double bond N, here double bond N. So this one is formed double bond N. Here it is having plus charge, here it is having plus charge, this is minus, this is minus. Now we have, it is having one more structure, that is this structure, this is N triple bond N, this is having plus charge, this is minus charge, this is N triple bond N, this is plus charge, this is minus charge. On heating of this compound, this one is eliminated. On heating of this compound, this one is eliminated. We get CH3 C triple bond C, CH3 plus 2 moles of nitrogen. This is butane ion is formed. That is alpha diketones when it is treated with the hydrazine. So we get that is butadiene. So this is addition followed by elimination. This is called condensation reaction. Carbonyl compounds undergoes condensation reactions. So followed by heating of HGO, elimination of nitrogen takes place. Nitrogen is a good leaving group, and we get that is butadiene. So this is alkyne from alpha diketones. Then next one is Fischer reaction. Fischer reaction. So this is Fischer reaction. So what is this reaction? Fischer reaction. This is nothing but one halo 2,2 dialkyl diphenyl alkenes, one halo 2,2 diphenyl alkenes are treated with strong base, we get alkynes, Fischer reaction. In this one halo 2,2 diphenyl alkenes are treated with strong base, we get alkynes. So here in this one, let us take example. So this is benzene, and this is C double bond C, and this is also benzene, Here this we are taking toluene, para-toluene group, and here this is hydrogen, this we have Br. Now we are labeling this carbon C14, Fischer reaction. So in this one, what happens? First of all, it is treated with strong base. This is CH3, CH3O- K+, it is heated. This is potassium tertiary butoxide. Potassium tertiary butoxide, it is a strong base. So what we get? This is the compound. The compound is this compound. This is a CH3, C triple bond C. This is C14, and this is C6H5. Now see the mechanism. In this mechanism, so this is C6H5, C double bond C. This is a C6H5. Here it is para position CH3. This is H. This is Br. Here this is a potassium tertiary butoxide. This is a base. This base abstracts this proton, and here loss of H+. We get this is C6H5. This is benzene, and this is para-toluene group. This is a para-toluene group, and double bond, here it is minus, this is a Br. In the next step, what happens? The negative charge is migrated here. The total phenyl group, this is a 14, C14, this is also C14, this one is migrated from here, and then Br minus is eliminated. Sir, we have two groups. Which group is eliminated? That is anti-group with respect to Br. Anti-group is migrated. So we get C triple bond C, this is C6H5, then this is C6H5, this is CH3, this is C14, This is called Fischer reaction. In Fischer reaction, one halo 2,2 diphenyl alkenes are treated with strong base, we get alkanes. This is called Fischer reaction. In this Fischer reaction, so that is strong base abstract proton, and with respect to Br or with respect to living group, so that is anti-group is migrated. So this is Fischer reaction. This is preparation methods of alkynes completed. So after preparation methods of alkynes, so the next one is chemical properties of alkynes. Already we are discussed some chemical properties of alkynes in alkenes only, that is hydration, that we are finished there. So chemical properties of alkynes. So here CH triple bond CH, we are going to discuss, that is regarding acidic nature, acidic nature of alkynes. CH triple bond CH, CH2 double bond CH2, CH3 single bond CH3. The carbon hybridization is sp, if the carbon hybridization is sp2, the carbon hybridization is sp3. As the percentage of S character, here the percentage of S character, first of all percentage of S character. Actually, as the percentage of S character increases, electronegativity increases. If electronegativity increases, polarity increases. If polarity increases, acidic nature increases. Here this is carbon, this is carbon, this is carbon. We have 3 carbon, but the 3 carbons do not having same electronegativity. Actually, electronegativity of atom also depends on hybridization. Here the percentage of S character is here 50%, here 33.3%, and here this is how much, 25%. The percentage of S character is less, here the percentage of S character is more. As the percentage of S character increases, as the percentage of S character increases, that is electronegativity increases, then acidic nature also increases. That means that is acidic nature of alkynes is greater than alkenes, alkenes is greater than alkanes. This is terminal hydrogen, this terminal hydrogen having acidic nature, this terminal hydrogen having acidic nature. So therefore, this due to this acidic nature, not all alkynes, alkynes should have compulsory one acid alpha hydrogen, acidic hydrogen, that is generally terminal alkynes having acidic nature, that is acidic nature of terminal alkynes is greater than non-terminal alkynes. So due to this nature, this forms acetylides. Suppose if you take acetylene CH triple bond CH, when it is treated with sodium liquid ammonia, sodium in liquid ammonia, sodium in liquid ammonia, what happens? These hydrogens are replaced here. We are taking excess, two sodiums are replaced, two hydrogens are replaced by two sodiums, that is C minus, this is minus, and this is plus, this is plus. This is acetylide. So if it is treated with Cu2Cl2, Cu2Cl2 by NH4OH, here we get that is C, this is Cu, C triple bond C, Cu. This is a red precipitate, this is a red precipitate dicopper acetylide. This acetylide reaction, this reaction, it is used for the differentiating between terminal alkynes and non-terminal alkynes, similarly terminal alkynes and alkenes. If it is treated with Tollens reagent, that is AgNO3 plus NH4OH, this is nothing but Tollens reagent, Tollens reagent. Ammonical silver nitrate, that is called Tollens reagent. So what happens? These two hydrogens are replaced by silver, we get CAgC triple bond CAg. This is a white precipitate is formed, white precipitate is formed. This reagent and this reagent, both reagents are used for the differentiating between terminal alkynes and non-terminal alkynes. Suppose we have CH3 C triple bond CH, we have CH3 C triple bond CCH3. So how can we differentiate? We can differentiate by using these reagents. First of all, for example, AgNO3 plus NH4OH. Here acidic hydrogen is present, therefore it gives white precipitate, whereas here do not gives white precipitate due to absence of acidic hydrogens. Similarly, that is Cu2Cl2, Cu2Cl2 plus NH4OH, Cu2Cl2 plus NH4OH. It gives red precipitate, whereas it do not gives red precipitate. Why? Because here acidic hydrogen is present, here acidic hydrogens are absent. Similarly, these reagents are used for the differentiating between alkynes and alkenes. Suppose if you take CH3, CH double bond CH3, this is a alkene, this is a alkene. We have terminal alkyne CH3, C triple bond CH. This is a terminal alkyne, here acidic hydrogen is present, here acidic hydrogen is absent. So suppose if it is treated with AgNO3 plus NH4OH, NH4OH do not gives any white precipitate, whereas it gives white precipitate. Similarly, Cu2Cl2 plus NH4OH, Cu2Cl2 plus NH4OH, it do not gives red precipitate, whereas it gives red precipitate. So this is a reaction with what this acetylides, and also this acidic hydrogen is also used for the to convert lower alkynes to higher alkynes, lower alkynes to higher alkynes. How can we convert lower alkynes to higher alkynes? Suppose I have one compound CH3 C triple bond H, this is propyne. Now I want to convert this molecule into CH3 C triple bond C, CH2 CH3, 1, 2, 3, 4, 5. This is 2-pentyne, this is 2-pentyne. So how propyne is converted into 2-pentyne? Now take that advantage, acidic nature advantage. CH3 C triple bond CH, it is treated with sodium. What happens? This hydrogen is replaced by sodium. So what we get? This is CH3 C triple bond C, minus plus byproduct is, that is here this is Na plus, and the byproduct is hydrogen gas. So this one now it acts as a nucleophile. Now this acts as a nucleophile. This is a strong nucleophile if it is treated with that is CH3CH2I, CH3CH2I. So now we need this part, Now we are taking ethyl iodide. This is a nucleophilic substitution reaction. This is a primary alkyl halide. Primary alkyl halide undergoes SN2 reaction, whereas tertiary alkyl halides undergoes SN1 mechanism. This nucleophile attacks here this carbon and elimination of I minus takes place. What we get? This is CH3, C triple bond C, CH2, CH3. This is a nucleophile. Suppose if the same nucleophile, if it is treated with carbonyl compounds, what happens? Here in this one, this is a nucleophilic addition reaction. This is a nucleophilic addition reactions. This nucleophilic addition reactions. Ademo nucleophilic substitution reaction. This is a nucleophilic addition reactions. So what happens here in this one? This is O minus, this is C triple bond C, CH3, then addition of H plus. So what we get? This is alcohol is formed, OH, C triple bond C, CH3. That means this is used for the conversion of lower alkynes to higher alkynes. This is also used for this acts as a nucleophile, and it is used for the preparation of alcohols when it is treated with ketone. So this is converted into alcohol. This is a nucleophilic addition reaction. Miscellaneous reaction. Suppose acetylene gas. When acetylene gas is passed through red hot iron tubes, what happens? Trimerization takes place. We get benzene. Suppose if this acetylene, it is passed through nickel Cn taken 4 or Cn taken twice on heating. So here tetramerization takes place. We get a cyclooctatetraene. This is a cyclooctatetraene, cyclooctatetraene. This is called COT cart. Cyclooctatetraene, here 1, 2, 3, 4, 8 pi electrons are present, but it is not a anti-aromatic compound, it is a non-aromatic compound. Due to loss of its plenarity, the shape is what? The shape is tub shape. It is not having, that is a planar molecule, it is not a planar molecule, this is having tub shape. Due to loss of its plenarity, cyclooctatetraene is not a anti-aromatic compound, it is a non-aromatic compound. So this is what chemical properties of alkynes. So after alkynes, this is chemical properties of alkynes completed. After alkanes and alkenes and alkynes, the next one is aromatic hydrocarbons. Aromatic hydrocarbons. So here aroma means fragrance. Aromatic hydrocarbons, when it is burned, it gives sooty smell or sooty smoke. It gives heavy smoke. Why? Because due to more percentage of carbon. Here aromatic hydrocarbons we can classify, that is according to Haeckel's. Compounds can be classified into 3 types, that is aromatic compounds, non-aromatic compounds and anti-aromatic compounds. But according to Haeckel's rule, aromatic compounds. Which compounds are called aromatic compounds? According to Haeckel's rule, those compounds obeys the following rule, that compounds are called aromatic compounds. So what is Haeckel's rule? Compound must contains 4n plus 2 pi electrons. Here n may be n equal to 0, that means 2 pi electrons. If n equal to 1, then that is 6 pi electrons. N equal to 2, that equal to 10 pi electrons. If n equal to 3, that equal to 14 pi electrons, etc., etc. So, according to Haeckel's, if any compound, if it obeys the following rules, that compounds are called aromatic compounds. So, the first one is compound must contains 4n plus 2 pi electrons, and compound should be cyclic compound. Compound must be cyclic. Compound must be planar. Compound must be planar. Compound must contains conjugated system. Conjugated system. So, compounds, so according to Haeckel's, those compounds which follows or which obeys the following rules, that compounds are called aromatic compounds. 4n plus 2 pi electrons, compound must be cyclic, compound must be planar, compound must contains conjugated system. These compounds are called aromatic compounds. And those compounds which follows the following rules, that compounds are called anti-aromatic compounds. Anti-aromatic compounds. According to Haeckel's, the first one is compound must contains 4n pi electrons. Here n is not equal to 0. If n equal to 1, that means how many pi electrons? 4 pi electrons. If n equal to 2, that is how many pi electrons? 8 pi electrons. If n equal to 3, that equal to how many? 12 pi electrons. If n equal to 4, that equal to 16 pi electrons, etc., etc. Second one, only the first rule is different. The first rule is different. So, here all 4n plus 2 pi electrons, there 4n pi electrons. Here the compound is cyclic, this is also cyclic, compound must be cyclic. Here compound must be planar, here also planar. Here compound must contains conjugated system, here also compound must contains conjugated system. Conjugated system. Only the difference between aromatic and anti-aromatic, that is 4n plus 2 and 4n pi electrons, the remaining all rules are same. And the next one is non-aromatic compounds. Non-aromatic compounds. Which compounds are non-aromatic compounds? Those compounds which do not obey Haeckel's aromatic and anti-aromatic, that compounds are called non-aromatic compounds. Let us discuss some examples. Let us discuss some example which compounds are aromatic and which compounds are anti-aromatic, which compounds are non-aromatic. Let us discuss some examples. Let us apply all the rules on examples. Now, see here. So, first one is, if you take cyclopropene, this is a cyclopropene. In this cyclopropene, how many pi electrons? 2 pi electrons are present. Here 2 pi electrons are present, but complete conjugated system is absent. Therefore, this is a non-aromatic compound. This is a non-aromatic compound. If we take cyclopropene, cyclopropenyl cation, this is cyclopropenyl cation. Here plus means there is no electrons, it contains 2 pi electrons. It contains 2 pi electrons. 2 pi electrons, here conjugated system is present. It is a cyclic, double bond, single bond, positive charge, single bond, double bond. That means conjugated system, and it is a planar molecule. Therefore, this is a what if n equal to, that is 4n plus 2 n equal to 0. That means this is a 2 pi electron. This is a aromatic. This is a aromatic. This can also be represented like this. Okay, like this plus. Next, after this one, cyclobutene. Cyclobutene. In this one, it is having only 2 pi electrons. It is having 2 pi electrons. That is, conjugated system is absent. Therefore, this is a non-aromatic compound. This is a non-aromatic compound. Next, if we take cyclobutene, that is butynyl, that is butadienyl cation. Here how many pi electrons? This is having 2 pi electrons. This is having 2 pi electrons. Double bond, single bond, positive charge, single bond, positive charge, single bond, double bond. That means conjugated system is present, therefore, this is a aromatic compound. This is a aromatic compound. Suppose if we take cyclobutene dinyl anion, negative charge is nothing but 1 pi bond. 1 pi bond is nothing but 2 electrons, that is 2 electrons. So 2, 2, 4, 4 plus 2, 6 pi electrons. This is a 6 pi electrons. 6 pi electrons means if n equal to 4n plus 1, n equal to 1, 4, 4 plus 2, 6 pi electrons. This is a aromatic compound. It is aromatic, that is also aromatic compound. These aromatic ions are called quasi-aromatic compounds. Quasi-aromatic compounds. Quasi-aromatic compounds are nothing but aromatic ions. Aromatic ions are called quasi-aromatic compounds. If you take then cyclobutadiene, this is a cyclobutadiene. Cyclobutadiene, it is having 4 pi electrons. It is having 4 pi electrons. 4 pi electrons, it is having conjugated system. This is a anti-aromatic compound. Anti-aromatic compound. Actually, this is a less stable compound. This is less stable compound, and it exists as a at room temperature. At room temperature, it undergoes dimerization. It undergoes dimerization. That means, so this is anti-aromatic compound. This is one anti-aromatic compound, and this is one more anti-aromatic compound. What happens here? This is dimerization takes place. We get a non-aromatic compound. This is a non-aromatic compound. Non-aromatic compound. Now, let us continue some more examples regarding aromatic and non-aromatic and anti-aromatic. So, here this is cyclobutadiene. It is a anti-aromatic compound, less stable. Therefore, at room temperature, it undergoes dimerization. It is converted into non-aromatic compound. Similarly, this cyclobutadiene, it also reacts with active metals like lithium, sodium, potassium. What happens? This is one electron, a sodium active metal, it gives this electron, and these pi electrons are migrated. So, we get here double bond, this is negative charge, this is electron. Again sodium gives one more electron. So, here what happens here, double bond, this is negative charge, this is totally 6 pi electrons. 6 pi electrons means this is a aromatic compound. This is an anti-aromatic compound is converted into aromatic compound. These anti-aromatic compounds are also undergoes dimerization. This is converted into non-aromatic compounds. Similarly, let us take cyclopentadiene. In cyclopentadiene, we have how many pi electrons? Here we have 4 pi electrons. In this one, 4 pi electrons are present, double bond, single bond, double bond, single bond, double bond, single bond, single bond. That means here conjugated system is absent. If the conjugated system is absent, therefore, this is a non-aromatic compound. Actually, it should be anti-aromatic, but here conjugated system is absent, therefore, this is a non-aromatic compound. Suppose if we take cyclopentadiene anion. Cyclopentadiene anion. Anion means negative charge. Negative charge means 2 electrons. 1, 2, 3. 3 to ja 6 pi electrons. This is a 6 pi electron. 6 pi electrons means it is a aromatic compound, and conjugated system is present. It is a planar molecule. This is a aromatic compound. Suppose if you take cyclopentadiene cation. Cyclopentadiene cation, what happens? That we will discuss now. See here, in this one, suppose cyclopentadiene cation, how many pi electrons? Here we have 4 pi electrons, that is conjugated system is present. Now, this is a anti-aromatic compound. This is a aromatic compound, this is a non-aromatic compound, that is a anti-aromatic compound. So, this example, cyclopentadiene, this is cyclopentadiene anion, that is a cyclopentadiene cation. So, these three are different. So, the same family, One is having positive charge it becomes anti-aromatic, negative charge it becomes aromatic compound, and without charge that is a non-aromatic compound. Let us take benzene. This is a benzene. How many pi electrons? This is 6 pi electrons, and this is a benzene. The name of this compound is benzene, and it is aromatic. Why? Because it is a planar molecule, and here that is 6 pi electrons are present and conjugated system is present. So, if we take this one, this is a cyclooctatetraene. This is a this is called COT. COT is nothing but cyclooctatetraene. Cyclooctatetraene, it is having 8 pi electrons. It is having 8 pi electrons. Conjugated system is present, but it is a non-aromatic compound. So, why it is a non-aromatic compound? Due to loss of its planarity. Everybody is thinking that this is a planar molecule, but actually it is not a planar molecule, it is a non-planar molecule. It is a non-planar molecule. Due to loss of its planarity, actually it exists in tub shape. It exists in tub shape. This is a non-planar molecule. It is a non-planar molecule due to tub shape. That is this is which molecule? This is not a non-aromatic, this is not anti-aromatic, this is a non-aromatic compound. It is important. Cyclooctatetraene is not an anti-aromatic compound, even though it is having 8 pi electrons, but it is a non-aromatic compound due to loss of its planarity, tub shape. And next, here these are what? Monocyclic compounds. Let us discuss some more examples, that is heterocyclic compounds. First of all, let us discuss heterocyclic compounds and also polycyclic compounds. First of all, that is polycyclic compounds. If you take this benzene, benzene is a monocyclic. If you take naphthalene, this is called naphthalene. This is naphthalene. Naphthalene is also aromatic. Naphthalene. This is naphthalene. After this one, this is called anthracene. 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 1, 2, 3, 4, 5, 10 pi electrons. 10 pi electrons. Here 1, 2, 3, 4, 5, 6, 7, 14 pi electrons. Conjugated system is present. This is called anthracene. Anthracene and naphthalene, these are also aromatic compounds. Next, after anthracene and naphthalene, let us concentrate on heterocyclic compounds. Heterocyclic compound, heterocyclic compounds. This is a furan. This is called furan. This is called furan. In this furan, we have double bond and 2 lone pairs. So, in these 2 lone pairs, even though oxygen is having 2 lone pairs, but we are considering only 1 lone pair. The second lone pair, it is not, even though it is in conjugation, that is not considered in conjugation. Why? Because only 1 lone pair participates in delocalization, the another lone pair is not participating in delocalization. Therefore, here that means total pi electrons are 6 pi electrons. 1, 2, 2 to the 4, 4 plus 2, 6 pi electrons, 6 pi electrons, this is a aromatic compound. Furan is a aromatic compound. If you take thiophene, thiophene means instead of oxygen we have sulfur. In this sulfur again also having 2 lone pair, but we are considering only 1 lone pair, that is in delocalization. How many pi bonds? 2 to the 4, 4 plus 2, 6 pi electrons. This is also 6 pi electrons, this is also aromatic. This is also aromatic. Furan is a aromatic compound. Thiophene, this is the name of this compound is thiophene. Thiophene is also aromatic compound. 6 pi electrons, 6 pi electrons. And next, if you take this is a pyrrole, this is a pyrrole or pyrrole, this is a pyrrole, pyrrole or pyrrole. Here also we have 6 pi electrons, this 6 pi electrons, this is also aromatic, this is also aromatic. If you take pyridine, this is a pyridine, so this pyridine, double bond, double bond, double bond. Here we are not considering this lone pair is in delocalization, already we have that delocalization in between pi bonds. So here we have 6 pi electrons, 6 pi electrons, this 6 pi electrons, this is a aromatic, this is aromatic, this is called pyridine, this is called pyridine. Pyridine is an aromatic compound, pyrrole is an aromatic compound, thiophene is an aromatic compound, furan is an aromatic compound. So these are heterocyclic compounds. What are heterocyclic compounds? These are the cyclic aromatic compounds which contains other atom along with carbon it contains other atoms. దీనిలో కార్బన్తో పాటు మిగతా ఐటమ్స్ కూడా ఉంటాయి. వీటిని ఏమంటే heterocyclic compounds. These are aromatic examples. So now suppose if you take this one example, this is called azulene. Azulene is nothing but one is 7-membered, another one is 5-membered. One is 7-membered, another one is 5-membered. This is double bond, and here this is double bond, this is double bond. This is called azulene. So this azulene, it is an aromatic compound and it is having dipole moment. Here it is having dipole moment. Here dipole moment is not equal to 0. Dipole moment is not equal to 0. It is having some dipole moment and it is soluble in polar solvents. Next, these are some compounds we are discussed, that is which is aromatic and which is non-aromatic. Let us apply some more examples, that is so where free rotation is possible, where free rotation is not possible, that we can apply now. Suppose we have this is a compound, this is double bond, and here it is, this is double bond. Now our question is, here free rotation is possible or not? This compound is having dipole moment or not? So that question first of all. Sir, how can we identify it is aromatic or non-aromatic or anti-aromatic? Very simple. So here this is one ring, this is one ring. In between these two rings we have one double bond. Migrate the pi electrons towards any ring. Let us migrate this pi electrons towards this carbon. So what we get, this is here this is double bond, and here this is double bond. This is we have negative charge. This we have positive charge. Why? Because this is losing electron, it is gaining electron, therefore it is having negative charge, that is having positive charge. Now the total electrons 2 plus 2 4 pi electrons. This is it is becoming anti-aromatic compound. This is also becoming anti-aromatic compound. That means these pi electrons never be migrated from 5-member to 3-member side. Then what's that? Now we have to migrate these pi electrons to this side, to 3-member to 5-member. What happens? So you see here, this is a 5-member ring and this is a 3-member ring. Here double bond, here double bond. This is having negative charge, this is having positive charge. 2 plus 2 4 plus 2 6 pi electrons, and this is having 2 pi electrons. That means this is becoming aromatic compound and this is also becoming aromatic compound. That means totally it is an aromatic compound, and here this is more stable, this is having charges, therefore this is mu is not equal to 0. Mu is not equal to 0. So next, let us apply one more example here. Suppose we have this is a 5-member ring and it is fused with 7-member ring. It is fused with 7-member ring. So what happens here? Which side we have to migrate? Let us here migrate from here to here. So what we get? Migrate the pi electron such that compound should get stability. Here double bond, here also double bond. This here, this is a 7-member ring. Here double bond, double bond, double bond. Here this is having negative charge, this is having positive charge. And the total electrons are 2 plus 2 4 plus 2 6 pi electrons, here 6 pi electrons. This is 2 plus 2 6 pi electrons, this is 6 pi electrons, this is also 6 pi electrons, and this is aromatic and this is also aromatic. That means here free rotation is possible, here also free rotation is possible. Free rotation possible or not? Yes, first of all free rotation possible, free rotation is possible, and here its dipole moment mu is not equal to 0. And here this is polar or non-polar, it is a polar compound. So this is a free rotation, regarding free rotation. So after this free rotation, in some questions we have like that questions, కొన్ని ప్రశ్నలు కొన్ని క్వశ్చన్స్ ఎలా ఇస్తాడు, ఎలా అంటే సో ఇది రియాక్షన్ జరుగుతుందా లేదా అలాంటి క్వశ్చన్స్ ఇస్తాడు, దాన్ని మనం ఎలా ఐడెంటిఫై చేయాలి. ఫర్ ఎగ్జాంపుల్ హియర్ this is double bond, Here we have Cl. Suppose if it is treated with AgNO3, white precipitate is formed or not. Second one, it is treated with AlCl3, reaction takes place or not. What happens here? Ag plus, it needs Cl minus. Suppose if it is takes Cl minus, this is Cl minus, that means it is eliminating with its electron pair, it is going with its electron pair. So what happens here? We get this is double bond, it is positive charge plus AgCl precipitate is formed. If it is AgCl, now here how many pi electrons? 2 pi electrons, conjugated system is present, that means this is aromatic compound. That means this is, when compared to this one, this is more stable. Therefore, here this compound easily reacts with AgNO3 and AgCl, white precipitate is formed. White precipitate is formed. AlCl3 plus Cl. AlCl3 plus Cl, what we get here? This is plus charge and we get AlCl4 minus. AlCl4 minus. Again it is having how many pi electrons? 2 pi electrons. That means is it aromatic or non-aromatic? Therefore, this compound AlCl3 reacts with this compound, AgNO3 also reacts with this compound, we get this compound. That is what this is cyclopropanyl cation, this is also cyclopropanyl cation. So, therefore, reaction takes place. Suppose if you take this compound, here we have I. If it is treated with AgNO3, is it gives yellow precipitate or not? AgCl is a white precipitate, AgI is a dark yellow precipitate. Dark yellow precipitate is formed or not? Here this is I minus. If I minus means it is eliminating or it is removing or it is eliminating in the form with its electron pair. That means is it having positive charge or not? If it is having positive charge, what happens? Let us see. Here double bond, here it is positive charge. 2 plus 2, 4 pi electrons. 4 pi electrons means it is an anti-aromatic compound. It is an anti-aromatic compound. That means this reaction is not possible. Why? Because here AgI precipitate is not formed, yellow precipitate is not formed. So, this is what some type of reactions. So, after this reactions, now we are going to discuss, that is what is that? So far we are completed, which is aromatic and which is non-aromatic and which is anti-aromatic compound, where the reaction is taking place, where the reaction does not takes place. So, what are the conditions? And so, we are discussing one example, that is cyclobutadiene undergoes dimerization. Cyclobutadiene also reacts with metals. Similarly, cyclooctatetraene also reacts with metals and is converted into aromatic compound. Next, then now we are going to discuss, that is methods of preparation of aromatic hydrocarbons. Aromatic hydrocarbons. So, first of all, that is from alkanes. Sir, how alkanes converted into aromatic compound? Is it possible? Yes, it is possible, but it is not a direct step. For aromatic compound, suppose if you take benzene, benzene requires 6 carbons. So, minimum we are taking 6 carbon atoms, that is hexane 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. This is nothing but N-hexane. N-hexane, when it is treated with Cr2O3 plus Al2O3 on heating, 1, 2, 3, 4, 5, 6, this is cyclohexane, this is N-hexane is converted into cyclohexane. This cyclohexane, again it is treated with Cr2O3 plus Al2O3. So, here we get that is benzene is formed, or it is treated with selenium, that is also converted into benzene. Next, second one, from alkenes. Yes, from alkenes, is it possible or not? Yes, it is possible. How can we? So, we have, that is Diels-Alder reaction, Diels-Alder reaction. So, in Diels-Alder reaction, so what happens? Diels-Alder reaction is nothing but conjugated dienes reacts with dienophile. It gives adduct. So, let us take conjugated dienes. This is cyclobutadiene plus this one. What happens? This is a 1,4 addition reaction. We get this is cyclohexene. This cyclohexene, when it is subjected to aromatization by treating with selenium, so we get So, what we get? This is we get here it is benzene is formed. This benzene is formed. This is a Diels-Alder reaction. Diels-Alder reaction is like generally takes place between conjugated dienes and dinophiles. Not only this one, here this is from alkenes. After alkenes, next one, third one, this is from alkynes. When acetylene gas, CH triple bond CH, when acetylene is passed through red hot iron tubes or copper tubes, here 3 moles undergoes trimerization, we get benzene. This is nothing but C6H6. Or similarly, CH3 C triple bond CH, this is called propine. Propine, when it is passed through red hot iron tubes, we get that is mesitylene. Mesitylene is formed. CH3, this is CH3, this is CH3, this is mesitylene. Mesitylene is formed. So, Diels-Alder reaction, it is main reaction. Actually, this is conjugated dienes, and dinophile. Conjugated dienes required electron releasing group, whereas dinophile required electron withdrawing groups. Generally, dinophiles, not only this is the alkynes are also acts as dinophiles, and also benzene also acts as a dinophile. Benzene also acts as a dinophile, not benzene, benzene also acts as a dinophile. So, this is dienes requires electron releasing groups and dinophile requires electron withdrawing group. Actually, it is a syn addition, and in this reaction, that is the symmetry of the reactant never changed. That means it is a stereospecific reaction, that is preparation of aromatic compounds. This is from alkanes, this is from alkenes, this is from alkynes.